All right, folks. Well, welcome back. I hope that you were able to have a fairly good weekend. I know that there's a lot going on outside the classroom, outside of what we have to do in our work here. That obviously will distract us from our work, but hopefully we can set that aside for a little bit here and focus in on what we have to do to finish out the semester. Like I said at our meeting, we're going to try to finish up the semester here and focus in on what we'll have to do for the final next week. And so if you have any questions, please make sure if you need follow up on what we talked about at our meeting, stop by after class today, after the lecture day, and at 1:30 and get clarification on that. Okay. All right, so let's go ahead and finish up here with this concept of free fall, and then I want to go ahead and finish up with projectile motion to round out the semester here, and move forward with what we have to do. Okay. All right, so we left at this problem on Thursday, and it allowed us to practice and see how we could apply what we know about a free falling object to the problems here. Okay. And so we talked about then three types of free falls, that an object can fall freely towards the earth in three different manners. Okay? What they all have in common then is that the acceleration will be constant, that each of those types of free fall have the exact same type of acceleration, which is negative 9.8 meters per second squared. The reason why all three types of free falls then have that acceleration is because the only force acting on those objects then in their motion as they move in this free fall is the force of gravity. We ignore friction, and as a result then, an object is dropped from a height above the ground, an object that's thrown down, and an object that is tossed up. All three of those types of motions is referred to as a free fall, because all three of them, if we ignore friction, if we ignore drag force, the air friction, will be falling towards the earth, and as it does so, it is going to be accelerating at a rate of negative 9.8 meters per second squared. Okay, and so what we have to be able to do as we work through these problems then is identify what type of, how the object is free falling. Okay, and so in this first example here, we saw then that this is an example of the first type of free fall, in which then what characterizes the first type of free fall is that it starts at rest. And remember, the first type of free fall, an object is being dropped, which means that it has no velocity as it's moving down, and it starts to speed up because of the acceleration of the earth, the force of gravity pulling down on the object and thus accelerating it, speeding it up. Okay. All right. And so we worked through this problem here. We worked through this problem, and I asked you to, and we saw then using the kinematic equations, we can solve for this displacement. And I asked you to use the third kinematic equation in order to solve for displacement as well. Okay. And the third kinematic equation, I'm just going to go ahead and start with that. Okay. The third kinematic equation then gives us this form here, which we have then V final squared is equal to V initial squared plus 2A delta Y. Okay. Now we were able to say then that we could use this equation here. Okay, so I'm sorry, let me use that marker here. Okay. We were able to use this particular formula, and remember there were three kinematic formulas which you have to make sure you remember. We could apply all three kinematic formulas here because a free falling object is an object that moves in one direction. It's a one-dimensional motion with constant acceleration. And remember, kinematics is the study of one-dimensional motion of an object moving in one dimension with constant acceleration. And so we were able to identify then, remember on Friday, just Thursday as a recap, we were able to identify that this object is moving at the first free fall. Okay, we were able to identify that this is a free-falling object that is being dropped, which means then the initial velocity is going to be 0 meters per second. Okay. We were told then that the time interval in which we are considering, and I'm sorry, let me go ahead and do this here. Let me list it for you. That the time interval here is a 1.5 second time interval, and that since this is a free fall, they do not tell us, but what we do need to know then that the acceleration is constant, and that constant acceleration we designate with the letter G, but the value then is 9.8 meters per second squared, and the negative indicates then the direction of the acceleration, which is downward. Downward is going to be negative, okay? All right, so this is what we got from the problem. And so what we were able to do from the problem is we were able to solve for V final. And so with V final, then we were able to solve for it as being negative 14.7 meters per second squared. So we solved for this. The first three here we were given. So these three we were given in the problem, okay? And this one we calculated for. So we calculated for the final velocity. But now that we have the final velocity, okay, we can solve for the displacement. They also wanted us to find the displacement. So we were able to solve displacement using the second kinematic equation. We found then that that displacement was 11 meters, negative 11 meters because it's downward. Okay, so this was also calculated as well. But I asked you then to calculate for this displacement using this third kinematic equation, because there is your displacement. Okay, so you can also use, you should be able to use this equation to solve for displacement. Why? Because we have the acceleration. Why? Because we have the initial velocity. And why? Because we have that final velocity, which we solved for here. Let's go ahead and let's plug it in, and let's solve for our final velocity, our displacement. Okay, in order to solve for the displacement, we have to rearrange this equation. Okay, so solving for displacement, okay, rearranging this equation, we have to subtract v initial squared from both sides and divide by 2a. Okay, so writing that equation out, if you're not quite sure how we get this, please make sure you come by and see me. Okay, so it's going to be v final squared over v initial squared minus v initial squared all over 2a. Okay. Make sure then, if you're not clear on how we derived this equation from this formula, you come by and you see me, because it's absolutely necessary that you're able to do that for the exam next week. Okay. All right. So at this point, then it's just a matter of plugging in these our values. So v final then is going to be negative 14.7 meters per second, and we have to square that whole thing. Okay. So make sure the negative is underneath the inside the parentheses here. Okay. Minus v initial, which is 0 meters per second, and we have to square this whole thing as well, and that's all over 2 times the acceleration here, which is negative 9.8 meters per second. Okay, and we square that. Okay, and so you plug that into your calculator, and lo and behold, folks, you get your answer then rounded to 2 significant figures as negative 11 meters, which we expect should also happen. Okay, this should support what we were able to get here. They have to give you the exact same answer. Okay. All right. Very good. So make sure you, if you need to, pause the video, okay, and go find your work here from Thursday and compare your work to what we just did here. Okay. All right. Let's move forward and let's continue practicing more of these problems here. We need to practice more of these problems here to get you to see then how we can apply kinematics to this. Okay. So let's take a look at this problem here. Okay. Take a look at this problem here and take a look at it. Read it first. Okay. Identify what type of motion it is. Identify what you're given, and then go ahead then and work through the problem. Okay, so let's take about 5 minutes to work through this problem here, and then I will work it out with you. Okay, so go ahead and start on this problem. Okay, let's go ahead and let's see what we have here. Okay, so we have an object that is, so our coin is being flipped. Okay, which means that we are tossing this coin upward. This is a free fall. This is the third case of the free fall. So this is free fall number 3. Let me go ahead and write that in here. This is free fall number 3, which is an object being tossed up. Okay, so that's what distinguishes the free fall number 3. Okay, so what we're looking at here then is, if you take a look at this, we are looking at the upward movement. We're going to divide this. Remember, the free fall number 3 is the tossed up and then comes back down. In this particular problem here, we are only looking at the upward trajectory. So this is being tossed up. Okay, so that's what we're looking at. We're looking at the first half of this free fall here. So again, first of all, this is free fall case number 3, in which the object is being tossed up, and then it falls back down. What we're focusing on in here is only the object being tossed up. Okay, and so we're told then that the object reaches a high point, and that high point is at 0.25 meters above where you started. Okay, And so they're asking you then here, what is the initial speed? So they're asking you to solve for V initial, okay? That's what we're given in this problem, okay? What we have to do now is we have to apply what we know about free fall and fill in whatever else we need, and then solve for that unknown initial speed there. Okay, so that's what we know. Let's go ahead then and let's solve for this problem. Okay, let's go ahead and solve for this problem. Okay, now let's work this out and let's compare answers. Okay, all right. So like I always said, make sure then you draw the situation first. Okay, so let's draw the situation. Here's our coin, okay, of mass m, and what we're doing is that we are tossing it in the upward direction. So we're moving in that direction. Okay, so that's the motion there that we are examining. Okay, all right. So we are told then that when it reaches the top, right here, when it reaches the top of the pathway, okay, it has traveled a distance here of delta y 0.25 meters. Okay, so this distance here is 0.25. So from where it starts right here to where it reaches the top is 0.25. Okay. All right. So with that said, let's fill in what we are given. Okay. So we are told then, besides this, that's it. That's all we are given, that it's tossed up. What we have to be able to do then is we have to fill in the missing details based on what we know about this free fall. So first of all, this is a free falling object. So what do we know about the acceleration? We know the acceleration is constant, and that constant acceleration has a value of negative 9.8 meters per second squared. Okay. Then we also know then that the velocity here at the height, which I'll designate v sub h, the velocity at the very top of the pathway, and that's what it's saying, that it reaches that top at 0.25 meters, is going to be 0. Remember, the objects have to stop and then come back down. And so that's what happens when you toss an object upward. Okay. And so at the very top here, it reaches a height of 0.25, but it stops and then it comes back down. And so that is what we know. We know that based upon what we're given here. So this is what we're given. This was not given, the velocity here. And this acceleration was not given. It was assumed that you know that. And so that's why I was telling you, you have to be able to memorize the different characteristics of the 3 types of free fall. So you have to have that, or else you're not going to be able to solve for this problem. Okay. All right. So with that said, what do they ask us to solve for? This velocity here. And so the object must have an initial velocity. Okay. Remember, the initial velocity is what's considered when the object leaves your hand. So as the coin leaves your hand, not when the coin is resting on your hand, because when the coin's resting in your hand, it has no velocity. But when you flip it up, the moment when you flip it up and it loses contact with the hand, that's when it has its initial velocity. And that's what they're asking us to solve for. Okay. All right, so let's go ahead then. So this is motion in one direction, in one dimension, with constant acceleration, so we can apply the kinematic equations. So let's go ahead and list the kinematic equations that we know, the 3 of them. V final equal to V initial plus A times T. Okay, let's go ahead and list the second one. It's going to be delta Y. It's going to be equal to VT plus 1/2 A T squared. Okay, and then the third one then is going to be V final squared is equal to V initial squared plus 2A delta Y. And remember, all I did here was change out the y, x's for the y's. Okay, but these are essentially the 3 kinematic equations we learned a couple of weeks ago. Okay, all right. So the question is, which one of these equations will give us V initial? Okay, and the other thing is give us V initial in the simplest way possible. Okay, well, let's go ahead and what we have to do then is figure out then which one of these equations will have V initial in it and has the other, and we are given the other 3. Okay, all right. So let's go ahead and take a look at this one. So this one has V initial in it, so that looks good so far. Okay, we have V final if we consider then that this represents the final motion, the final velocity for this particular motion. The idea then is, if the way you want to imagine this is that we hit the pause button right when the coin gets to the top. Okay, and so the motion here, we will isolate only between the initial point here and this final position right here. So therefore, this represents then our V final. Okay, our V final as well. Okay, All right, so with that said, then we have v final right here. Okay, we have the acceleration right here, but what are we missing? We're missing time. Okay, so we can't use this, and we don't have time. So this won't work for us. Okay, all right. How about this second equation here? Okay, this second equation doesn't even have the initial on it. Okay, so we can't use this one at all. It doesn't have the initial. So we are left with this equation right here. We are left with this equation right here to solve for v initial, because here we have v initial. V final is considered this right here. So we have v final. We have the acceleration here, and there is our displacement. So we will use this equation here in order to solve for our v initial. And that's the process of deduction that you have to use in order to find the correct equation, the correct formula to use to solve for the problem. So good. Now that we've gone through that process, we can go ahead and let's plug it in and solve for that particular equation. Okay. All right. So taking this equation here, we have to rearrange it to solve for v initial. So let's go ahead and rearrange to solve for v initial. If you notice here, solve for v initial, we have initial v initial squared is going to be equal to, that means we subtract 2a delta y from both sides, can be equal to v final squared minus 2a delta y. Okay. Now we want to solve for v initial. This gives us v initial squared, so we have to take the square root of both sides, which gives us then v initial can be equal to the square root of v final squared minus 2a delta y. Okay. All right, so there it is. We have the equation that we need in order to solve for our v initial. So let's go ahead and plug in the values that we have. Okay. So folks, again, if you're not quite sure how we get from the first equation here to the second equation, okay, or from this the formula here to this first equation, you need to come by and see me, or make sure you practice that algebra. This is just simple algebra here, folks. Okay. All right. So let's go ahead and plug in our values. So we have the square root then. V initial is, v final is this point here. That's considered 0 meters per second. So that's going to be squared. Okay. Minus 2 times the acceleration here, which is negative 9.8 meters per second squared. Okay. And the displacement here, the distance that it travels here, which is going to be positive, it moves in the positive direction, positive 0.25 meters. Okay. All right. So you go ahead and plug in those values into your calculator, and you end up then with a value that is 2.2 meters per second. Okay. And that is your initial velocity at this point here. And so that's how we go about solving for these problems involving a free-falling object. Okay. All right. So compare that to your what you did. Make sure you write this down. Okay. And I would like to work out another problem for you. Let's keep this moving. Okay. So let's go ahead and let's take a look at another problem here. Go ahead and take a look at this problem here. This is still based off the coin that we talked about, okay, in the previous slide. Okay. And work this one out. Okay. And so the question now is this. Okay. If you flip that coin, and now we're going to look at the downward trajectory as well. Okay. The question then is, how much time did it spend in the air? What is the time that it spent in the air? A little bit different. I think a little bit more challenging. Take about 5 minutes to work through this problem here, folks. Okay. And then we'll finish up with this problem. I'm going to work this problem out for you, and then we'll finish up with it. Okay. So start this problem right here. Okay. This problem is a little bit more challenging, okay? But do make sure you understand then that this is still, and let's go ahead and write this down, this is still free fall number 3. This is free fall number 3, which is an object that is tossed up, okay? Free fall number 3 represents an object that is tossed up, okay? However, this time though, we're looking at the upward and downward trajectory. We're looking at both of those, okay? All right, and so what we were told then is the same height, so we were given the height, okay? So that from the previous problem, make sure you keep that in mind, okay? Now the question is, what we're solving for is time, okay? We're solving for time, and we are asked to find out the total time interval that the object spends up in the air, okay? All right, so with that said then, let's go ahead and let's work through this problem. And what I'd like to do then is I'm running low on time here. And so what I'm going to do is I'm going to draw the picture for you. Okay, let's go ahead and let's analyze this problem here. And I want you to be able to um, um, work out this problem. Okay, so let's go ahead and let's analyze this problem together. Okay. All right, so let's draw the image of the object here, image of the picture here. Okay, so we have our coin here, and what's happening with this coin here, and let me see if I can find, no. Okay, what's happening with this coin here is we are following it on its upward trajectory, and then it comes back down, and what they're telling you is that it lands in the exact same spot that it took off on. And so you'll notice here that this is a symmetrical motion. That means then if we take a line and if we split this object, we split this motion in half. And let's take a look at this. Okay, the upward motion mirrors the downward motion. Okay, the upward motion mirrors the downward motion. So what I would like you to do, and we'll finish up with this problem tomorrow, take a look at the slide that we have about this. And what does that slide tell us about the time up, okay, and the time down, okay? And I want you to refer to that in order to help you with this problem. And so we said then with this since this is a free fall, the acceleration then is constant, and it's going to be negative 9.8 meters per second squared. We also know that the velocity at the height here, so we'll call this v sub h, is going to be 0 meters per second. And then we know then that at the height here, at the very height here, okay, it reaches a distance, and we'll call that displacement, of 0.25 meters. Okay, so we know that as well. Okay, and then the question is, we remember also, we know the initial velocity from the previous problem we solved for. We know the initial velocity here as being 2.2 meters per second. Okay, so we know all that now moving forward. How can we find, and they want you to find the total time that the coin spends in the air. Okay, given this information, how do we go about solving for that? Okay, so please make sure you work this one out, and then try your best with this. If you weren't able to get this far on your own, now that I have it listed here for you, try to work this one out. We will go over it tomorrow, and then we'll continue on doing more of these problems. Okay, so very good. Go ahead and make sure you get that done, and then I will see you folks tomorrow. Okay, have a good day.